We can apply Newton's laws to analyze the motion of an object. In this case, we use the concepts of mass and force to determine the acceleration of the object. We can then use the acceleration to determine the velocity and displacement of the object after a given period of time. Newton's laws are useful to analyze motion and to make predictions about the final state of an object's motion. But we can also analyze the motion of objects in a different way. We can look at motion from the perspective of work and energy. The concepts of work and energy are scalar quantities, so they have no direction associated with them. Since these two quantities are scalars, they are often easier and faster to deal with than our vector quantities. So energy can be a useful tool when solving kinematics problems. This is because energy is a conserved quantity. Energy is a scalar quantity and easier to deal with. And energy is a useful concept not only in the study of motion, but in all areas of science. At Naledi High School in Soweto, Mr. Shokat Ali Ismail is discussing a problem which involves the motion of an object.
One way that we're going to use is by using vectors, and the second way that we're going to do it is by involving energy equations.
The intended outcomes for this lesson are to be able to use the principle called conservation of energy to solve motion problems, which would be complex to solve using kinematics equations, and that the understanding of the concepts should lead the thinking of learners rather than the equations.
Well, the original intention was to ensure that we find a final velocity of an object when it falls down, but by using two methods. The difficult one was to use vectors, where you have magnitude and direction when it comes to vectors. But an easier way would be to use energy equations. And with energy equations, you're just finding velocity without interfering with direction at all. The first thing that we're going to do is just test your knowledge. Find out what do you know about energy, about work, and so on.
In this first activity, the learners are presented with a worksheet containing various scenarios that they must discuss in their groups.
The first part of the lesson was to just conscientize them on concepts on energy and work. They have to differentiate. They have to just find out what is work, which is applying a force and an object moving over a certain distance.
A duck tries to swim upstream in a river. The river current is so strong that the duck does not seem to move with respect to the shore. Does the duck do any work?
No.
Yes, it does. It is trying to move, so...
But it's not moving.
Yeah, but something is done.
This is one of the stumbling blocks in the understanding of work. The teacher explains.
What's the formula that you use to calculate work done?
The force times the displacement.
Yes. Now, your full definition would be force times distance moved in the direction of the applied force.
Yes.
If you're standing at the shore,
Yes.
does the duck move?
No.
Although the duck is trying to move, but the movement of the duck is being cancelled out by the movement of the water.
Yes.
Now remember, the formula says work is equal to force times distance. If the distance is 0, meaning the duck is not moving, is work being done?
No.
No.
Is work done on the duck?
No.
Why?
Its forces are in equilibrium. And it's still in balance.
And again, the duck doesn't move at distance. And you know that work is the product of force times distance. If there's no distance or force, there's no work done.
The same duck is exhausted. She stops swimming and drifts away with the current. Is work done on the duck?
Yes, work is
done.
done. Work is done.
Yeah, because now the distance now is involved.
Yeah.
And the force.
And the force.
Okay.
Why do you get tired pushing hard against the wall even though no work is done?
But then you are using energy. That's why you get tired.
In another example, trucks are used to discuss work.
Okay. The big truck and a small truck, they are traveling with the same speed. Which truck of the two will take more work to stop it?
To stop an object with a greater mass, will need a greater force.
Yeah.
The interesting thing that I noted was the children have gone to the concept of work and energy within the classroom. But when it came to applying it to a normal problem out there, like a vehicle moving on a road, they had forgotten to use the equations to do the explanation. They were trying to explain from experience without bringing in the physical concepts.
A big truck and a small truck have the same momentum. Which truck of the two will take more work to stop.
In this example, the teacher gets learners to start thinking in terms of the concepts involved.
So what is momentum? Where's your formula for momentum? The momentum of the big truck will be its mass times its velocity. The momentum of the small truck. Eventually they started to understand that a problem out there that is not within the physical science classroom can still be explained with knowledge learned within the classroom. Now, what you know is that this mass is bigger than this one. Let's put a big mass.
Mr. Ismail makes up some numbers and substitutes.
That would be your big truck, remember that, okay?
Yes, sir.
Now let's put a smaller mass for the small truck. Let's make it 2 kilograms.
2 kilograms.
If you make, now remember the mass is big,
Yes.
here your mass is small.
Yes.
Now remember the momentum is still the same value. The logic tells you that if your mass is small, but its velocity has to be larger for it to obtain the same momentum.
Momentum, yes.
Okay, now, why did we do that? The reason for that was to relate it to work. And again, work done is force times distance, and force is mass times acceleration. The intention of the questions was to get you thinking on energy and work. How, when you are talking about energy and work, you're bringing in concepts of momentum, you're bringing in displacement, you're bringing in acceleration, all your other scientific concepts for motion is involved whenever there is energy. The reason for that is for you to have work, you must have a force and you must have displacement. That means there must be movement and there must be an applied force.
Science learners usually hesitate to use the concept of energy in problem solving because it is such an abstract idea. Here's an example of a motion problem which can be quite challenging to solve using the kinematics equation, but which can be very easily solved using the principle called conservation of energy.
Law of conservation of energy says energy can neither be created nor destroyed. But what happens to it? It's transferred from one point to another. So what we are going to do now is we're going to transfer that energy from potential energy to kinetic energy. So your mechanical energy, that means adding potential and kinetic, will always be the total value. Okay?
When we say conserving energy in everyday language, what we really imply is that we should save fuel rather than energy. In science, however, conservation means that a certain quantity remains strictly constant. We do not have to try to conserve it. In this activity, learners are required to determine the velocity of a marble rolling down an incline just before it hits the ground using energy equations.
Look at the activity.
They are presented with a worksheet containing clear instructions on how to present the experiment. A piece of piping is fastened onto the edge of the table using press stick. Next, a marble is rolled down the pipe. The point that it hits the ground is marked and is covered with a sheet of white paper and then carbon paper facing down. Now, when the marble is rolled down the pipe, its position is clearly marked.
Let me go see. Let's move that and see. So we should be getting a few marks, and then we will use the average spot mark.
The marble is released several times so that an average landing position is obtained. It is important for the variables in the experiment to remain constant. In this way, the margin for error is diminished.
When you talk in a classroom, you're basically talking to children and you're expecting them to visualize certain things. And different people visualize the same concept differently. And therefore, their understanding of the concepts become different. So with the practical, everybody is seeing the same thing. And when they're seeing it, then they're able to understand what they're seeing and interpret what they're seeing.
When the learners have rolled the marble 4 or 5 times and an average position is obtained, it is time to get measurements. The first is H1, the distance from the floor to the edge of the table.
Oh, it's 90 centimeter.
Centimeter.
And we have to convert it to
2 meters.
And why do we have to convert to meters?
I think velocity, our velocity is measured in meters per second.
There you go.
So, 0.9.
0.9.
The measurements on the floor from the edge of the table to the ink.
It's 87 centimeters.
Again, learners convert the measurements to meters. The final measurement is from the top of the pipe to the tabletop.
It's 36
centimeters.
0.36 meters.
When all the measurements have been obtained, each group returns to their desks to discuss their questions.
Comment on energy of the marble at position A. Potential energy is maximum at the top and is 0 at the bottom.
Right.
Then kinetic energy is 0 at the bottom.
This is not entirely correct. The teacher intercedes.
What do you need to find kinetic energy?
MS and velocity.
Mass and velocity. So let's not consider the work now. Let's consider velocity. Okay. Now, is this marble moving at A?
No.
No. It's starting with an initial velocity of 0. So if it is 0, what is the kinetic energy? 0. Right. What can you tell me about the height at position A? At A, it is the maximum, the most, isn't it? So if at A, your height is maximum, your potential energy will be maximum. And if at A, your velocity is 0, your kinetic energy is 0. Now, as the marble is rolling down, what's happening to its velocity? Velocity is increasing. Now, if the velocity is increasing, what can you tell me about the kinetic energy?
It's
The
increasing.
kinetic energy is increasing. Initially it was 0, now it's increasing. Right. What's happening to the height as it's going to be?
It's decreasing.
The height is decreasing. If the height is decreasing, what can you tell me about potential energy?
Potential
Potential energy is decreasing. What happened now to the height? Let's see.
decreases.
To what? It decreases to 0. So if at C your height is 0, what is your potential energy?
0.
What can you tell me about the velocity of the marble at C?
It's maximum.
Velocity is maximum. So if the velocity is maximum, all that potential energy that was here is converted completely into kinetic energy. That's what. All right. Now you've identified.
In the next question, the learners discuss the source of energy of the marble at position A.
It's from someone's.
The energy is coming from the person who is releasing the marble.
Does it also include gravity?
Yes, the gravity that you're getting is in the potential energy because as we're going to go down now, potential energy is mass times gravity times height. So
It is important to note that up to this point, the teacher has not mentioned formulae. He's ensuring that learners understand the concepts of energy conservation and transferal. The learners will now start to use the formulae to solve the problem.
what is the formula for finding the kinetic energy of an object? Right, write out the formula. EK.
Learners know that the formula for kinetic energy of an object is half mass times velocity squared, and for the potential energy of an object, it is mass times gravitational acceleration times height.
What is the energy at A? We're looking for the formula.
The formula is EP equals to mgh.
Times H1 plus H2.
Mr. Ismail emphasizes that to prevent errors, the exact positions should be mentioned.
Give me a formula that is now going to be used at B. But remember, we are dealing with mechanical energy. There is kinetic energy at B as well as potential energy at B, isn't it? So in that case, the formula now would be
EM is equal to mgh1 plus half mvp squared.
the velocity you're talking about here is the velocity of the marble at position B. So it is half mvb squared.
The formula for the energy at position C is then determined.
It's half mv squared.
Compare the energy of the marble at positions A, at B, and at C. Discuss if it remains the same or not, and justify your answer. Now,
Because we are dealing with mechanical energy, learners must determine the potential and kinetic energy at each of the positions and add them together.
your mechanical energy at A is equal to your kinetic energy at A plus your potential energy at A. Okay? Now, what is the kinetic energy at A? It is 0 because the object is stationary. Right?
The teacher substitutes 0 for the kinetic energy at A and the formula for the potential energy at A.
So in this instance, it is 13,5 m, which is now your total mechanical energy at A.
In the same way, the energy at C is determined by adding the kinetic and potential energy together. 0 is substituted for the potential energy. Mr. Ismail will now remind the learners of the law of conservation of energy.
Now we know, in terms of the law of conservation of matter, E, the energy, the mechanical energy at A, is equal to the mechanical energy at C. Right. That would mean whatever answer you get here, you will put it in here. And this answer, you will put it here, right? Let us go and substitute some values.
The teacher substitutes these values and comes to an answer.
Velocity is 5,19 meters per second. Is the velocity of C. All they have to do is understand the conversions from kinetic to potential and potential to kinetic. Apply the formulae, and they are away. They're able to work out formulae because the formulas are relatively simple and it's less formulae to use. There's not a lot of formulae to be applied.
Hello viewers at home, we have just watched a video on energy, work and power. We would just like to talk about this lesson, and today at the studio I have Liz, Andrew, and Feroza.
Hello.
Feroza, the teacher started the lesson by actually talking about the meaning of the words energy, power, and work. And he made the learners to actually use the worksheets and actually trying to find out how much they know about the meanings of this word. How did you find that activity?
You know, I always also try to start by trying to ascertain what the learners know. It's always wise to move from what is known to what is unknown. And it's pointless going on to more complicated concepts if learners don't have something basic within themselves to anchor their new learning on. So it was essential that he determine what they know about work, what they know about energy, so that he could subsequently lead on to very, very complicated work. I shouldn't use the word work again, onto very complicated concepts later on. So I thought it was, it was a very good technique on his part. Yes.
And what do you do if you find out that they don't understand some of the concepts that you are to introduce in a lesson?
Well, then it's obvious that you're going to have to try and, go over it properly and make sure that the learners have a pretty good idea of what you're going to be teaching them later. So you've got to make sure that the basics, the background is there.
Okay, and immediately after that, the learners were engaged in an activity. And how did you find that happening in the video?
I thought that was good, Tembi. I mean, again, the diagnostic question part of it. Assessment is very important, and sometimes we want to limit ourselves, to say, well, a diagnostic has got to be voluminous, it's got to be 10 pages or whatever. But just a few questions at the beginning is very good to determine where learners are. And I think in relation to the questions that were asked, he went straight into the activity to say, look, here's activity, think about it. What do you think? The learners were allowed to discuss. They were talking amongst themselves. But I think, for me, this is my own opinion, I felt that perhaps it really is a question of the structure of the worksheet. It didn't really engage the learners to discover things for themselves. Therefore, I found that the teacher had to come in every now and again to actually explain things from time to time. So I would have another look at the actual questions on the worksheet to make sure that they're such that they can elicit the learners to think and therefore to discover some of the things themselves, so that the teacher doesn't have to engage so much with them.
But do you think the experiment was an easy experiment for them to understand, where you had to use the pipe and other things?
No, I think the experiment was great. I mean, the learners were involved. They used the marble. Was it the marble? To roll the marble down. I think that got them involved. They observed, they engaged, they discussed. The teacher asked them several questions, about the potential energy. They were also involved, I think, in the measurements of the different parts to find age both ways. So I think it was very hands-on. And so, and whatever you do, Tembi, anytime in class, if it's hands-on, it always goes a long way to reinforce learning. So I think it was quite good.
And what do you think is the value of that the value of practical work in science classes?
Well, for one thing, it certainly imprints it in your memory. I'm sure the learners will remember that pipe and the marble rolling down. I thought one thing that was really good about this lesson too was the way the teacher linked the formulae with what was actually happening. I think so often in our current syllabus, what happens is that learners apply a formula, substitute numbers, do a calculation, but doesn't have meaning in terms of the actual physical reality of the situation. And by starting with this practical demonstration of rolling the marble down the pipe and then moving from there to the formula, I thought that was a very good link.
I also think so. And what do you think about the classroom management, Andrew? How was the class managed?
Well, yeah, it was well managed. I think the teacher was in control. You know, the times when he was talking to very small groups of learners, I think 4 or 5 that I could see, and obviously having other learners involved in other things. So I think the management of the class was very good. Although, I mean, you know, he could still have. Of course, the nature of the actual practical doesn't allow that. But I think giving out different roles to different people within the team, you know, asking somebody to make notes, record things, somebody else to be the one who actually probes perhaps and so on, measurement and so on. I didn't actually see the teacher do that, but maybe that happened behind the scenes, you know, to actually allocate specific duties within the teams. That helps with classroom management, because then you don't have people that are just, you know, not just doing anything, but just up to causing disturbance and creating problems in terms of managing the class.
I thought, as he said, that he was talking to small groups, but I found that he's talking to the small groups and he's questioning and he's leading them on was very good. And I was actually thinking that perhaps that could have been done with the class as a whole, you know, because it was really very excellent discussion, question and answer technique that he had going with them. And he brought in a whole lot of physical concepts, you know, be it momentum, acceleration, mass, etc. And I thought it was very worthwhile and something that the whole class should be able to listen to. And
don't you think it was captured by his summary at the end? Because at the end he had a summary on the board where he had all the results from the groups.
You know, that is true. I must say, I find his technique quite enjoyable and quite interesting, and I think, well, from looking at the learners, they all look to be very actively enjoying the lesson, I think. I thought it was very good.
Another aspect that I thought was good about the lesson was the fact that the apparatus was very simple. Hardly cost anything at all, and I would think that that apparatus would be accessible to just about every teacher. Not difficult to get that apparatus, and yet what they were doing was quite sophisticated in terms of the results that they were getting out.
I thought you were reading my notes, Liz. Just joking. But I was going to, I fully agree with Liz, and I was going to make that point as well, that often we're looking for very sophisticated equipment. You know, very expensive equipment, and everybody's saying, well, we don't have the budget for this, we don't have the budget for that. I want to use very fancy computers and computer analysis. Those things are useful, and they have a place in the whole educational spectrum. But I think there's a place where people use simple material, a material that they're familiar with, material they can make up themselves. They can literally do this experiment themselves at home and see that it even works at home. It's not something that only happens in the lab, you know, the lab syndrome. But, you know, simple equipment, powerful concept, very important. We need to do that more frequently.
And that's all we have for today. Thank you, Liz. Thank you, Andrew. Thank you, Feroza. Thank you, viewers at home. I hope you enjoyed the lesson. See you next time. Bye-bye.